Now that we've talked about what forces are, the next thing we have to figure out is for different types of forces, what's the direction that that force acts. We are going to do this for three main force types. So these are the things that we're going to be dealing with over and over again. The first one is the weight of an object. That is the force that gravity applies to the object. That is different from the mass. So the mass is a resistance to acceleration, but the weight is actually a force. The second one is pushing contacts, when objects push on each other at some boundary, across some boundary. And the third one is pulling forces. And we are always going to think of pulling forces as being applied by some kind of cable or string or rope. Okay? And as I'm describing the directions of these different forces, I'm going to describe them in terms of what's called a free body diagram. And a free body diagram is just a diagram where the only thing in the picture is the object that you're analyzing, and all the surroundings are only represented by the forces they apply to that chosen object. And so you're always going to have an outline of your chosen object in your free body diagram. You can do it as just a dot, you can do it as a circle, you can do it as the outline of the shape, but your object is always going to be in there. And then besides that object, all you're going to have is forces. Okay, so the first one we're going to talk about is the weight force. This is the simplest one. It's always the same direction. This is the force applied to the object by gravity. And the magnitude of this force is always mg, and the direction is always down. So it makes sense, I think, that gravity always applies a force downward. Mg, this m is the object's mass. And this g is the acceleration of gravity in free fall, 9.8 meters per second squared. Okay, so an object that has more mass has a bigger force of gravity applied to it. That's what you're feeling if, a small dog sits in your lap and it's comfortable, a giant dog sits in your lap and it's a little painful. That's because gravity is pulling harder on things with more mass. That can be a little confusing thinking about that in terms of our first common misconception. But remember that, so gravity pulls harder on heavier things, but it has to pull harder in order to make them accelerate. And the net result is that all things in free fall accelerate the same way, even though there are different forces pulling on things with different masses. And so for a free body diagram, and I'll just abbreviate this FBD, if this is your chosen object, you're going to always put in the weight force acting down, and you can write it in as mg, or if you know some of those numbers, you can put them in. If the object has a mass of 5 kilograms, then the free body diagram would look like the object with the weight force acting down. And the magnitude of the weight force is 5 kilograms times 9.8 meters per second squared, which is 49.0 newtons. And that's all we have to say about the weight force. It's the same for everything, just the mass of the object times 9.8 meters per second squared down. So now we're going to move on to pushing contact, pushing forces. And the direction of pushing forces is always perpendicular to the surface of contact and toward the chosen body. Okay, so let's see what this looks like in free body diagrams. Let's say that we have these two objects that are free to roll along a horizontal surface, and they're in contact with each other. And let's say there's a 50 Newton force acting this way on one of those bodies, and a 100 Newton force acting this way on the other body. And let's say this one has a mass of 1 kilogram, and this one has a mass of 2 kilograms. Okay, well, let's think about these bodies individually. For the 1 kilogram cart, what forces are acting? So I'm going to draw these as outlines. You don't have to do that, but I'm just doing this to make it clear. So, well, we have the weight force acting straight down. That's 1 times 9.81, so that's 1 times 9.8. Sorry, I'd leave the 1 out. So this is 9.8 newtons acting down. There's a 50 Newton force here. And then there are two places where the surroundings are pushing on this 1 kilogram body. The ground is pushing up on it. That's what prevents this from falling into the surface. And the 2 kilogram cart is pushing on it. And so we're going to follow the rules of directions for these two things. The pushing contact from the ground is perpendicular to the surface, so that's perpendicular to the ground, toward the chosen body. And unlike the weight, we don't know what the magnitude of these pushing forces is. We're usually just going to have to calculate those. So I'm going to give this a variable name for now. And this says that we don't know what the magnitude n is, but we do know that it's in the direction up. And now we'll look for the contact, the pushing force applied by the 2 kilogram cart. That's perpendicular to the surface, toward the chosen body. We don't know the magnitude of that force. I'm going to call it R for reaction force. But that's just a variable, and that's something that we would have to calculate later. And now let's think about the free body diagram for the 2 kilogram cart. There's a weight force acting down. So that's 19.6 newtons. There's a 100 Newton force acting over here. Notice that I didn't put the 100 Newton force in the 1 kilogram one because it isn't acting on the 1 kilogram. And I didn't put the 50 in the 2 kilogram free body diagram because it isn't acting on the 2. So you're only putting in the things that are acting exactly on that body that you're analyzing. Okay, now we're looking for places where there is pushing between these bodies. The ground is pushing up on the 2 kilogram cart, so that's perpendicular to the surface, toward the chosen body. And I'm going to call this N2 just because there's no reason that we would think that the magnitude of this force is equal to the magnitude of the force over here. And now we have the pushing force applied by the 1 kilogram cart, perpendicular to the surface, toward the chosen body. And now I'll give that name a variable. And notice that these two I gave the same name. Okay, I didn't do that with those N's, those normal forces. But when you have two bodies pushing on each other, the pushing forces on each one by the other have the same magnitude. And that's something really important. So I'm going to make a note of that here. So notice if body 1 and body 2 push on each other, the pushing force on body 1 has the same magnitude. In other words, you can use the same variable, has the same magnitude as the pushing force on body 2. The last type of force that we're going to see all the time is pulling forces. And usually these are going to be applied using cables. But even if they're not, so I'm going to write cables in here, but even in the cases where cables are not being used to apply these pulling forces, we're just always going to pretend that they are. So you can always, if an object is being pulled on, you can always replace that connection with an imaginary cable and just think about the behavior of that cable. So that's what I'm going to do. Okay, the rule for cable forces is the direction is parallel to the cable. So here's where I'm saying, like, even if there's not a cable involved, we're going to pretend like there is to visualize this, but it's parallel to the cable. And this time it's away from the chosen body. Okay, so let's think about this. Let's think of a case where we have a ramp and a cable that goes over a pulley, and we have a rolling cart here. Let's say this one has a mass of 2 kilograms, and this cable connects to the cart and then connects it to a hanging mass. Let's say this mass is 3 kilograms. Okay, so hopefully you can make sense out of my drawing here. We have this one cable that's connecting these two bodies. So what do the free body diagrams look like for these two things? I'm going to start with a free body diagram of the hanging mass. So this is for the 3 kilogram mass. Here's the outline of the body. The weight force acts down, so that's 3 times 9.8. So the weight is 29.4 newtons. And the only other place. You can just look at the body and look for anything else that's touching the chosen body. The only other thing that's touching the chosen body is this cable. And anytime you have a cable, it's a pulling force. So the rule is parallel to the cable, away from the body. And I'm usually going to denote pulling forces with the variable capital T for tension. And the tension itself is the magnitude of that pulling force. And that's all for the 3 kilograms. So now let's go to the 2 kilogram. And this one is at an angle like this. Okay, so what forces do we have? We have the weight force acting straight down. That's just what the weight always does. And that's 2 times 9.8 is 19.6 newtons down. Then the ground is pushing on the wheels. The incline is pushing on the wheels. And so we'll use the rules for pushing. That's perpendicular to the surface toward the chosen body. And I'll give that the name N. And then last, the cable is attached over here. The rule says parallel to the cable, away from the body. And I'm going to give that the variable T. Well, just like, I did with the pushing case, there is a reason that this and this are given the same name. Those always have to have the same magnitude. And so here's the rule for that. So notice, if two bodies are connected by the same cable, and notice in this case that cable went over a pulley. Whether it goes over pulleys, goes through pulleys or not, this is true. If these two bodies are connected by the same cable, the tension of the pulling force is the same on each body. Okay, let me do another example, get a few of these things in here. So let's say that we have a horizontal surface and a cart like this, and it's in contact with a second cart like this, and then this cart is connected by a cable to this one. And I'll give masses to all of these. Let's say this is 30 kilograms, this is 5 kilograms, and this is 20 kilograms. And it looks like these are hovering off the ground. Those are supposed to be rolling, though, that my wheels just didn't make it down there. And let's say that there's a force applied this way of 100 newtons. And we want to draw free body diagrams for each of these bodies. Okay, well, I'm going to start with the 5 kilogram. We have a weight force down of 5 times 9.8. So that is 49.0 newtons. We have a pushing force from the ground. So that's perpendicular to the ground toward the chosen body. I'll call that N5. We're going to have a lot of these pushing forces from the ground, these normal forces. So the different subscripts just mean that they're different variables. So after this, if I have an N20, it means that we don't know what the magnitudes of those forces are, but there's no reason to believe that they're going to be the same. And now you can look all the way around the body. The only other place where there's contact between this and the surroundings is a pushing force from the 20 kilogram. And so that's perpendicular to the surface toward the body. And I'll call that R. And that's it for the 5. And now I'll go to the 20. There's a weight force down of 20 times 9.8. So that's 196.0. There's a pushing force from the ground. I'll call that N20. And the only other, nope, there's 2 more places actually where there's contact. The 5 is pushing on the 20. And so that is a pushing force perpendicular to that surface toward the body. And since that is a pushing force between the 5 and the 20, that has to have the same variable name as that same contact force on the 5. So I'm going to call that R because I already called the one on the 5 R. And now the last thing is the pulling force from the cable. That's parallel to the cable, away from the body, and I'm going to call that T. Notice up until now that 100 Newton force hasn't showed up in anything because it wasn't acting on either of these 2 bodies, but it is going to show up in this free body diagram of the 30 kilogram. Okay, so there's a weight force down of 294 newtons. That's 30 times 9.8. There's the given force of 100 newtons. A force given like that means we're not told what's causing that force, but someone else in the calculation has already figured out that's what's applied. And so we just put that in there the way it's given. Then there's a pushing force from the ground up. I'll call that N30. And then last, there is a pulling force from that cable. The rule says parallel to the cable, away from the body. And since it's the same cable as the one attached to the 20, I need to use the same variable. So I'm going to call this P. And that's it. Those 3 diagrams represent all of the forces on each one of these bodies in that problem.